In this video, I'm going to show you how to implement a reduced state machine using OR and AND gates. In the picture here, we have three states. We have a state 0, 0, we have a state 0, 1, we have a state 1, 0, and each of these states outputs something to the user. State 0, 0 outputs X, state 1, 0 outputs X and W, and a state 0, 1 doesn't output anything. In order to go from state 0, 0 to state 0, 1, we need to assert A. In order to go from state 0, 0 to state 1, 0, we have to assert not A. In order to go from state 0, 1 to state 1, 0, we have to assert not A. And in order to stay at state 0, 1, we have to assert A when we are at state 0, 1. And if we are at state 1, 0 and want to go to 0, 0, no matter what we assert, we're gonna go there. So if you don't see a letter on top of the arrow here, it means that no matter what A is A or it's A not, it's gonna go to the state that the arrow is pointing at. Now I have to capture those information in my truth table. So if I'm currently at state 0, 0 and I assert 0, as you see, we're gonna go to state 1, 0. Now, when I was at state 0, 0 when I was at state 0, 0, what was the output? The output was X. So I'm gonna turn on X and turn off W. Now, if I'm at state 0, 0 and I assert A, I'm gonna go to state 0, 1. So I'm going to go to state 0, 1. Now, when I was at a state 0, 0, my X was turned on and W was turned off. Now, if I'm at state 0, 1, and I assert 0, I'm going to go to state 1, 0. And when I was at state 0, 1, X was turned off and W was turned off as well. Now if I'm at state 0, 1 and I assert A, I'm gonna go to state 0, 1 again, and X was turned off, W was turned off. Now if I'm at state 1, 0 and I assert not A, I'm gonna go to state 0, 0, and when I was at state 1, 0, W and X both were turned on. Now if I'm at state 1, 0 and I assert 1, I'm gonna again go to state 0, 0, and when I was at the state 1, 0, both X and W were turned on. Now I have another state in my truth table which I don't have in my state machine diagram, and that state is 1, 1. So that state is a don't care state. We don't care about what's gonna happen in that state. So no matter if I assert 0 or 1 for A, I'm gonna have like just X over here. So we don't care about what's gonna happen in these two states because we don't have it in our diagram. Now in order to reduce the logic, we have to use a K-map for N1, N0, X, and W. The way we do that is to say that if you're at a state 0, 0 and A naught is asserted, what's gonna happen to N1? So N1 is gonna be this guy here. If you're at a state 1, 0 and 0 is asserted, N1 is gonna be this guy here. If you're at a state 0, 0 and 1 is asserted, then N1 is gonna be this guy. If you're at a state 1, 0 and 1 is asserted, then N1 is going to be here. If you're at a state 0, 1 and 1 is asserted, N1 is going to be this one. If you're at a state 1, 1 and 1 is asserted, and 1 is here. If you're at a state 0, 1 and 0 is asserted, then if you're at a 0, 1 and 0 is asserted, then N1 is here. If you're at a state 1, 1 and 0 is asserted, N1 is this guy here. We're going to basically do the same thing for N0. Now that we're done with n1 and n0, we're gonna move on to x and w. So for x, we are gonna only consider the current states. So x is independent from the choice of a. So if you're at a state 0, 0, x is gonna be this guy here. If you're at a state 1, 0, then x is gonna be this guy right here. If you're at a state 0, 1, then our x is gonna be 0. If you're at a state 1, 1, then x is gonna be this guy here. Now for w, we basically do the same thing. If you're at a state 0, 0, w is 0. If you're at a state 1, 0, w is 1. If you're at a state 0, 1, then w is gonna be 0. If you're at a state 1, 1, then w is gonna be just we don't care. So let's put that one also. Now let's take a look at n1, n0, x, and w and find their reduced form. When we look at the table for n1, we have a 1 here and a 1 here. And remember, for k-maps, we can group the ones that are in 2's power. So if we have 1, 1, 1, or if we have 2, 1, or if we have 4 ones, or if we have 8 ones, we can group them. And also remember that for k-maps, we can wrap the k-map around. So if you wrap this k-map around, then 1 and 1 are going to be adjacent. So we can group these two. Let's say that we group them and we color them the same. We're going to also do the same thing for here. We're going to group these two ones and color them the same. The same thing for this one here. Color them the same. And in the last one, we have an x here. We have a 1 here. We have an x. This 1 is a don't care value, so it can to satisfy the purposes of the k-maps, we can also call this x to be a 1. So if we call that x to be a 1, then we can group these two and make the k-map be more efficient. One thing I want to also explain here is that what if we got something like this for n0, that here and here were x, here and here were 1, and all of these were x's. Now how would the k-map, how would the grouping would be different? If we have x's here, then we can also call these x's to be 1s. So then we're gonna have a huge chunk of 1s here that we can group. Let's say that we group them and we call them group blue. Also, you have to remember that this one is standing alone, so this one needs to be grouped with something if possible. We're gonna group this one and this one and call them to be one group. So this one is shared between the blue group and the yellow group, so I'm gonna call it to be red. So red is a shared value between the yellow group and the blue group. Okay, now let's come up with the formulas for each one of my variables. So n1 is gonna have s1 not changing between these two cells. So s1 not is not changing between these two cells. Also, a not changing between these two cells. So if I'm going from this cell to this cell, as you see, a not stays the same. So a not is gonna also be here, but I can't put s0 because s0 is changing from 0 to 1. Now for n1, I have s1 not changing, so s1 is between here and here, it's just s1 not, so s1 not, and then between here to here, s0 is changing, so I can't put a 0, but a is not changing. A stays with the same value, with the value of 1. For x, I'm gonna essentially do the same thing. as you see, S1 is changing from 0 to 1, but S0 naught is not changing. So S0 naught is going to be equal to X. And for W, I have S1 not changing from this step to this step. So S1 is gonna be the answer for my W. If I had this case here when my grouping was different for N0, the formula for N0 would be like this. So we have the same thing that we previously had. So S1 naught and A is going to be one of my groups, and then the other group consists of these four elements. So my S1 is changing from 0 to 1 when I go across this group. So I can't put my S1. My S0 is not changing in this group because S0 here is 1 and here is 1. So S0 is the element that I can put here, and A1 and A is not gonna be also in the expression because here I have A to be 1, here I have A to be 0. So I can't put A into this expression here. And that's how you would find the formula of when you had some case like this. So be careful how to deal with these x's and how to find the formula if you have a huge chunk of ones. Now let's implement the reduced state machine that we have found here using AND and OR gates. So here, as you see, I have an input of 0. So that is the 0 that is the A that we had in our diagram, and we have N which represents the next state, and we have S which represents the current state. We have a clock that helps us to change the state, and we have a reset button that it's going to take us back to state 0 whenever we press it. Here is the logic that we have implemented. As you remember, for N0 we had S1 naught, so S1, and then here is a NOT gate, and we had also A, so A is going to be here, and then because it's a multiplication between S1 naught and A, we're gonna have an AND gate, and the result is going to be N0, and N1 is going to be S1 naught times A naught. So that is how we're going to find N1. Then for our X and W, we have X equal to S0 naught, and then for W we're going to have S1. If we had the other case that we had here, so if we had N0 S1 equals to S1 naught times A plus S0, now we're going to implement that like this. So here this was the case. So let me just quickly show that. So if we had that hypothetical case, we're gonna change our logic to be something like this. So far we know that we had S1 naught and A, then we add our S0 to it. Now the logic is going to be like this. S0 is going to be added to our gate here, and then because we have an addition, that means we have an OR gate that relates these two quantities in our expression. So the answer of this AND is going to be ORed with S1, and if I attach this N0 to here, this is going to be my logic for N0. But we don't want to consider this case here. We want to consider the actual thing that we have found so far. Now if we are at state 0, 0, as you see, S1 and S0 both are turned off, then X is gonna be the one that is gonna be outputted. So X is glowing here. Now if I change A to be 1 and I hit the clock, as you see, it goes to the next step next state, which is the state 0, 1. And in state 0, 1, none of the X or W was output to the user. If I keep this as 1 and I clock it, as you see, it's not going to go to the next state, because do you remember we had like this arrow that is pointing back to a 0 to the state 0, 1. That is what we're doing here. Now if I change A to be 0 and I hit the clock, it's going to go to the next state, which was state 1, 0, and both X and W were outputted to user. And here it is. Then if no matter what I choose for A, it's gonna go to state 0, 0 again. So if I clock it, it's gonna go back to state 0, 0, 0, 0, which X was shown to the user and W was turned off. If I choose this one to be a 0, which means A naught, the state machine is gonna go to state 1, 0, which both X and W were shown to the user. Now no matter again what I choose, so let's choose this time to be to A to be 1, it's gonna go back to state 0, 0. Now I can also go to some other state, as you see here, and then if I press the reset button, it's gonna go back to a state 0, 0 no matter what.